In this segment, I'm going to be providing detailed explanations for many of the most commonly used program evaluation research designs, and I'll be talking through the different stat techniques that are used uh, uh, that correspond to each one of those designs, basically. And so this is really how to take a particular design and know which stat technique will best address the research question that is stemming from that particular design. And so these are all in SCC notation, or for the most part, and that means that every time there is an X, that means that this is the intervention, the program, or the independent variable that you are administering to individuals or manipulating, and then observing the effects, which is the O. So that O just means observation of the DV. And these can be taken both before for a baseline and after the intervention's implemented. So I'm going to go through each of these and talk about the different stat techniques and give you some tips, hopefully that will help you when you are putting together your own design and then and describing in the final project how to analyze it. Okay, so the first one is the most basic design, and it's not a very good one in terms of threats to validity, as we know, but a lot of times this is all that people can swing. So this is just two groups. One receives the intervention, one does not, and then there's just one observation at the completion of the program. So for this, we would use an independent sample t-test as indicated here. This is a simple two-group post-test only design. And in this case, we have the mean of individuals who were in the program. You know what, let me expand this a little bit. How about that? So just so we can see it a little bit better. I don't want to go too big, and hopefully that will help. Okay. So we have the intervention group's mean here, and we hope that it is significantly larger or smaller depending on if we want to increase an outcome versus decrease an outcome. And then we have the mean of the individuals who are not in the program. And then we would compare these two with an independent sample t-test to see which mean, see if these means significantly differ. Okay, so that one is pretty simple to do. If you have covariates, I didn't put this in here in the document, but just occurred to me now, if you have covariates with this, all you need to do is do a regression instead and dummy code the intervention as 0, meaning individuals who were not in the program, and 1, individuals who were in the program, and create that variable in your SPSS file, and then regress all post-test scores, or the DV, onto that 0, 1 variable, meaning the intervention, and then have your covariate, whatever that is. I assume it's a continuous variable, personality or intelligence or whatever else that you're testing with folks. And then you would want the B weight or the beta weight, either one, for the intervention, the 0, 1 variable, to be significant, because that means that the intervention explains unique variance in the DV or the outcome, even with the covariate there. So it explains uniquely even when controlling for the covariate, whatever that is. Okay, one group pre-post. This is another very common design where you have a baseline and then you administer the program, whatever it is, and then you collect the outcome variable from the same individuals. It's very important that these be matched. So you need the same individuals at time 1 and time 2. Now, if this is a special case in which you cannot get matched data, you can only get means from before and after, but they're not the same individuals, then you would just do a regular independent T rather than a dependent T or paired sample T, which we would do in this design with matched data. Again, so this is one group pre-post. If measures can be matched, this is a paired sample t-test. And again, if the data cannot be matched, if it's just aggregate or org level, department level data, depending on your particular study and program eval context, then you can do an independent T. If there are covariates, I suggest doing a repeated measures ANCOVA, and that is an analysis of covariance. And I don't do these very often, actually. ANCOVAs are not typically used in a lot of literature in our fields, at least, or our field, I should say. But they are important to know for program eval, at least have a reference point. And so I recommend this book by Andy Field, Discovering Statistics Using SPSS, and you can get it for fairly cheap. You can rent it for about 15, 16 bucks, and you can get one used for about 50 to have on your shelf for if you go into data analytics or program evaluation in your future life. I highly recommend that book because what it does is it walks you through exactly how to conduct an ANCOVA analysis and what to look for and how to interpret that data. And so if you ever need it, that's the resource that I would go to. All right, so that's the simple one group pre-post. Now there may be a certain situation in which you believe that there is another variable, and when people have a lot of that particular variable, they will gain a greater benefit from the intervention than those who do not have that. So for example, highly conscientious individuals will benefit more from the intervention than those who are not as conscientious. So that is where we have a program interacting with conscientiousness to predict the DV, whatever that is. And so in that case, this is an interaction or a moderation. And remember, a moderation is basically that the IV impacts the DV differently depending on another variable. And in this case, the intervention impacts the DV to a greater or lesser extent depending on conscientiousness. All right, so if the moderator is categorical for some reason and it has 3 or more levels, so that's not something I put here. If it just is dichotomous like gender, a 0, 1, thankfully we can do a regular regression. But if it is by department or by some other variable like that has more than 3 categories, then do a mixed ANOVA. But if the moderator is continuous, it's a little bit easier, like a personality variable, then we can do multiple regression in which we make an interaction term where your baseline or pretest is interacting with the intervention, and you would regress basically the post-test on both the intervention itself and the baseline separately, and then create an interaction term with the 0, 1 intervention variable multiplied by the pretest. And there are videos on YouTube. In fact, after I'm done with this screencast, I'll put in a link. Don't see it right now, but there'll be a link in there where I am going through how to create that interaction term and then analyze that. So I have a screencast on YouTube that goes through that. All right, so next is your 2-group pre-post, and this is again a very popular design. It is a very strong one in terms of addressing various possible threats to validity. So a lot of people go with this design if they can. And in this one, I find it easiest to just do a multiple regression in which the post-tests are regressed on both the pre-tests and our intervention, the 0, 1. And we hope that the intervention beta or B weight will be significant. That means that again that the program explains unique variance in the DV while even controlling for baseline. If you have covariates, that's very easy. You can just stick them into the equation. I would put them in a separate block so that you can look at the changes in the dV based on just the covariates alone, and then the baseline and the intervention. Actually, you put the baseline in the first step as well, the pretest, and then the intervention in its own block in the second step of the regression. So if you want to, in fact, I can probably stick a video in here as well where I conduct basically a regression that's blocked in that way. It's called the hierarchical method, and it basically gives you incremental change in variance explained in the post-test due to uniquely to that intervention, and that's very helpful. And clients may want to know what that is, and by doing this analysis you can provide that for them. And also you can talk about this particular analysis in interviews when people ask you, okay, here we have this design, how would you go about analyzing that? And you can talk through those steps. So again, intervention goes in the second block or the last block, and we would look at the change in R squared for the intervention effect, that incremental variance explained, which is usually what our clients want to know. One group double pretest design. So that is this down here. Okay, so this is one group double pretest, and remember this helps us rule out some threats to validity when we can't have two groups, an intervention and a control, because we can get some trends going between observations 1 and 2, and then we can check to see whether that whether this intervention creates change above and beyond that baseline interval. So that's the goal there. And for this, we want matched data. That means, and that's tough because a lot of times people don't want to fill out measures this many times, but if they're very short measures, that's helpful. And we need that matched all the way through. So people here, we can match them to people here and then to here as well. So all the way through. Use, in that case, with measures being matched, using a repeated measures ANOVA is very helpful. And if you have covariates or control variables, same idea. Do a repeated measures ANCOVA, which is an analysis of covariance, which is done when you have, you want to run an ANOVA, but you have some continuous covariates. For that, I forgot to mention earlier, you want to make sure that those covariates do not interact with any of the measures, so there's no moderation there, but Field goes through that and makes sure that you have those assumptions taken care of before you run the analyses. So again, he's very helpful. I use him for reference all the time myself because I can't hold all of these little details in my head about every different kind of analysis, and because there are some assumptions unique that go to each one, then sometimes I don't remember, etc. That's normal. Going to the reference is always good. Field talks about how to create a contrast to test the hypothesis that the change between observation 2 and 3 will be greater than the change between 1 and 2. There are ways to do that with plan comparisons, and again, I don't do these every day, but as a program evaluator, if that is your role in the future, you'll want to know how to do that. At least know where to go for reference always. Obviously, we don't always pull this information out of our head each time, but you can go to trusted sources like Field. There are some unique assumptions to this kind of test that Field talks about in Chapter 13. Now, if you have at least 30 individuals at each time point, and there are at least 3 time points as there are here, I suggest a longitudinal multi-level model analysis instead of an ANOVA or ANCOVA because MLM is a better technique. It will give us more accurate data, and it's just really nice for these kind of situations. It's a little bit complex and it goes beyond Field, however, so I suggest I didn't plan on doing this, but I have to show you. There is a book that I find very helpful by Ronald Heck and Scott Thomas, and it looks like this, and it's called Multi-Level Modeling with SPSS, and it provides very detailed instructions on how to run multi-level data for your particular study. And I have found this book helpful when I've had to run MLM stuff in SPSS. So you do need SPSS. You can't do it in Excel, like some of the analyses we've already talked about. It's also possible to do this in R, but this book won't help you do it in R. You'll need another book for that, and I don't have that off the top of my head, but if you would like that, I can always find it for you. So that is the story with MLM. Okay, so with MLM, we have nested observations. So we have time points, 1, 2, and 3, that are nested within the higher level, and that is individuals. And that means individuals take multiple measures over time. That's all that means. So MLM is helpful for nested data. Nested data just means that we have, for example, people nested within teams, nested within departments, and nested within organizations. So it's really like a group level an analysis that's created and meant especially for group level data. And that was created because if we don't acknowledge and account for the fact that we're using groups and that people within a certain group share certain characteristics, certain experiences, when we don't account for that, we make errors in inference later. And so this technique accounts for those things. If your measures cannot be matched, again, just simply do independent t-tests. I would do comparing this change to this change, and if they're both significantly different, then that's an issue, because that means that we can't tell if this intervention caused the change between 2 and 3, or if it was something else that was also causing changes in here. So I would say what we would want for that, just common sense wise, what we would want is no significant change here, and then some kind of change going on here. So that would be the goal that we would want to see. It'd be the pattern of results that would be most desirable as a program evaluator that we would want to find. All right, now we have a 2-group double pretest, and this gives us a little bit more information than this analysis, or design I should say, up here, where we just had one baseline observation. And so here this gives us a chance to compare this interval with this interval across the groups, and then compare this interval with this one as well. So that's helpful because it can help us to rule out local history, local maturation, etc. Or tell if that's happening at least. So it doesn't fix it, right? It just tells us if it's happening so that we have something to say to the client, and then a way to move forward to do a redesign later, basically. All right, so if the measures can be matched, which hopefully they can be, do a mixed ANOVA. A mixed ANOVA just means that you have a between subjects variable and a within subjects variable. The within subjects variable are these time points observations, because we have multiple ones of those on the same people. And then the between subjects variable is the one we really care about, and that is whether the intervention is working or not. And so that's again a 0, 1 dummy coded variable. For the mixed ANCOVA, again, Field has some good stuff on that. So just follow the instructions that he gives in that book. Basically what he has us do is look at the, don't have to create it, thankfully, in this analysis like we do in regression. So it's really helpful. You just look at the time multiplied by intervention interaction, basically. And we would expect the intervention to have an effect only between time points 2 and 3. So you could track that and do a mapping in SPSS of that effect to show it visually, and then also test it for a significance. So see Andy Field's book, Chapter 14, for that example. for examples of that. Again, MLM is good for this. Again, if you have 30 plus people at each time point, and there are at least 3 time points, then I suggest using MLM for that. The switching replications design is kind of interesting. Remember, it is this idea that you have time 1 and time 2, and you give the intervention, and then at between time 2 and time 3, the intervention is removed, or there isn't an intervention that is given. For a second group, let's say we have 2 groups, it's reversed. So between time 1 and time 2, there's no intervention, and then we give it to that group of people later between time 2 and 3. And then we have 2 points of comparison. We have between time 1 and 2, we'll compare groups, and then we expect them to flip from this interval, time 2 to time 3. All right, so I believe you can create a contrast code to do this. It's not important all the details of how to do that. I think Andy Field gives some tips for how to do that if you need to do it. And again, if you can run an MLM, do so. Again, that's 30 plus people at each time point, and then at least 3 time points, which we have here. Now, if the measures can't be matched, just do independent t-tests for the groups between time 1 and time 2, and then do another separate t-test for time 2, time 3. That's totally doable. And your pattern of results should look like, in that case, that you would have one group doing significantly better than the other in this, between this time point. So this would be whichever group got the intervention, and then it should be reversed at these time points. Interrupted time series. This one can get pretty complex, so I'll just give you the basics of this. If the measures can be matched across all of these time points, which a lot of times doesn't happen, it seems like the more time points we have, of course, the more attrition we have, and likelihood that we will not be able to keep the same cohort of people across all that. So again, remember, interrupted time series is usually done on archival data where we have, crime in a city across time or things like that. So it's more, I would say, macro in focus. The people who do program evaluations who use this design usually do more macro kinds of things, like societal level, like legislation or different policies that affect a community of people more than just an organization or department. And so, but if the measures can be matched, do an MLM design. But if the measures cannot be matched, like for example, I've had students in the past do projects where they're trying to reduce turnover over a certain period of time, like years, and they look at trends and what's turnover doing now, let's capture that, let's get a snapshot later, a few months into the future, and then we're trying to look for trends when we implemented this intervention. Did it move the dial on turnover in some way? So you can do eyeballing that, which is not the best, of course, but it's better than nothing. Or you can conduct independent sample t-tests between, of course, the intervention what is this? This space and time where the intervention is implemented. And that interval, I guess, is the term I was looking for. So the intervention interval, and then you could also do t-tests between observations 1 and 2, 2 and 3, etc. And you're conducting multiple independent t-tests, basically, and hoping that there is a change within this interval, and then a change within this interval as well, 4 and 6. And those kinds of things you can play around. It's a little bit more exploratory than some of the other designs that we have here. Exploratory in nature. Try to do your best to adjust for type 1 error if you do this. So if you're doing, I would say 2 or 3 are fine, just leave it at 0.05. But if you're doing 10 or so different analyses, then you have to think about, okay, you know, the probability of finding something purely by chance is increasing, and so maybe you want to bump that p-value down to 0.01 or 0.001. Regression discontinuity design. You need a minimum of 200 for this design as per Shatters, Cook, and Campbell instructions. So what you do is you analyze this with an ANCOVA, but I do it with regression as well. Regression can do an ANCOVA, so they're like the same thing. So you code the intervention 01. And then remember, with regression discontinuity, what we do is we take the mean of a cutoff variable, whatever that is, and everyone below the mean, we assign them to the intervention, and everyone above to no intervention, or vice versa. And this is a great design because it mimics random assignment, and it's so helpful when your client wants maybe the most needy individuals to have the intervention, or the most bright individuals to have the intervention. And that particular desire is so harmful for causal inference, as we know. And so this is a design that can get around that, where as long as the cutoff is adhered to explicitly and exclusively, then we can make some great causal inferences off this design. So the way that we do the analysis for it is code the intervention 01. Again, just 0 means no one in the group got the intervention, and 1 is those people did receive it, and then subtract off the value of each pretest score. So subtract the mean off if you have the cutoff at the mean, or whatever the cutoff value that you make. Subtract that off each of the pretest scores, okay, or the assignment variable, and that's what this is here. Observation A, OA, is the assignment variable, and then the C is just means that units or people are assigned to conditions based on adhering to some kind of cutoff, and then O2, of course, is our post-test. All right, so what we do is run the regression analysis, and we regress these post-test scores on two things. First, the intervention, the 0, 1 variable, and then second, the assignment variable with the cutoff score subtracted from each one of those. And you do that in SPSS. It's pretty easy. And then you end up with the two B weights. You have the intervention B weight and then the assignment variable or pretest B weight. And we want the intervention one to be significant, because that basically what this analysis does is it gives us that break in the regression line at the cut score. So it gives us an estimate of the intervention's effect right at the cutoff, which is what we care about, and what the client will want to know is right at the cutoff, where the groups are most similar, on the assignment variable, did that intervention move the dial on the DV? Note for designs with dichotomous or categorical DVs. So this is just in general. This doesn't necessarily apply just to or solely to regression discontinuity, but dichotomous DVs are a little bit more of a hassle to deal with, I would say, and they are basically where we're trying to predict a category that a person will fall into based on their involvement in the intervention. So, for example, we want to know if our IV causes a mock juror to assign a guilty verdict to a mock defendant, for example. Guilty versus not guilty. That is a dichotomous DV. What other things are... maybe we're trying to predict whether or not someone will choose to do something. We want to predict their decision on something, and it's an either or. It's not like a scale from 1 to 7 or something like that. So with categorical or dichotomous DVs, run a logistic regression, and Field Chapter 8 has great examples, practice data. In fact, I have a screencast with, I think, one of his examples where I walk through in SPSS how to do that. So if in your future you have any kind of situation where your client wants you to predict a yes/no kind of variable, an either or, don't panic, there are ways to do it. And even with three categories, if you're trying to predict which of the three categories someone will fall into, maybe a yes or no or an undecided, I don't know, just off the top of my head. Actually, I don't see this too often where we have this in the literature, categorical DV with three or more categories. But there is a way to analyze that, and that's through multinomial logistic. And Field on chapter, in same chapter, I believe. I'm not sure if it's chapter 8, but the page number is 301, so you can go there and look at what he did for multinomial stuff. Okay, well that is finally the end of our long document. I hope this is helpful to you as you're thinking about different designs. So when you're choosing a design, of course, for the study, the primary that you want to do for your client, the primary thing to keep in mind is threats to validity. And you know those best because you know the context of your study. What are the different things that could mimic the intervention's effect, make it look like it was effective when it was not, and how can we set up a design with proper controls that will rule that out. And so I've given you the basic ones here that you can think through. And then once you've chosen the design, the next step is to think about how to analyze that design using these various stat techniques. So good luck with that process, and the TA and I are, of course, here to help you in all of the stages through that process.